In this section, we look at putting lagged predictors into our dynamic regression model. So a lag predictor is used when a change in the X variable doesn't necessarily affect Y instantaneously. And the effect of X may linger for a while. So examples might be sales and advertising. So advertising spent in this time period may result in sales in a future time period. It gets used in hydrology and modeling stream flow and rainfall, because the rain doesn't necessarily end up in the stream in the same period in which it falls. It might take a few days or even weeks before the rain ends up in the stream. It gets used in farming, in modeling the size of a herd based on some quality predictor for the breeding stock, because you spend some money on getting good breeders, and it takes a while before that leads to calves and an increase in herd size. So whenever you get this lagged effect of the predictor, we can put lagged values of X into the dynamic regression model. X is sometimes thought of as a leading indicator if it's not having an instantaneous effect on Y, but it's having an effect in future values of Y. So when we write down the model like this, we can put in the present value of the predictor like this, and we can also put in lagged values of the predictor going back as far back as we want to go to. And then the error term, as usual in a dynamic regression model, is an ARIMA process. We can write that using backshift notation like that. And when we write it like that, this gamma operator is called the transfer function, because it describes how change in X is transferred to Y. And importantly, in these models, we're thinking of X as a fixed predictor. That is, it's a known quantity, and it's influencing Y, but Y is not influencing X. It's an exogenous variable in that sense. If we wanted it to go in both directions, X affecting Y and Y affecting X, we'd need a different type of model, a multivariate model. Let's look at an example using advertising and insurance quotes. So this data set comes from a US company where they were putting money into television advertising, and they were hoping that that would turn into people calling up to ask for a quote on insurance. So they were interested in the effect on quotes of their ad expend. So we can see the data here over a few years, and you can see that the series tend to move together. The ups and downs tend to coincide, which suggests that advertising spend is having an effect on quotes in the current month. What we're interested in is also having an effect in subsequent months. So here's a graph of quotes, advertising quotes against television advertising expenditure. And you can see for lag 0, there's a very strong relationship. So current advertising affects quotes in the same month. Lag 1, you can see that there's still a positive relationship. So advertising last month is affecting quotes in this month. It takes people a while to call up and get a quote. Lag 2, so that's advertising 2 months ago. There's no obvious effect there in the graph. That doesn't mean that there's not there in the data, but we can't see it in this particular visualization. So we're going to fit a range of models with different numbers of lagged advertising in them, starting with no lags, 1 lag, 2 lags, and 3 lags. And we're going to compare these 3 models, but because of the lagged nature of the predictors, that means that there's going to be missing values for the first few when we fit these for the first few residuals, because you can't lag further back than time 1. So to make them comparable, we have to ignore the first 3 values of quotes so that we can deal with a lag of 3 in the last model. Obviously, the first model, in fact, the first few models, we don't need to ignore 3 values, but to make them comparable, we need to ignore all 3 values. Okay, so let's see how well this did. So here is the AICC statistics and other information from the models. And we can see from the AICC statistic that the best model is this one with lag 1. So that includes current advertising and advertising from one period ago. So we're going to refit the model using all of the available data, not using the method we used before where we set some to missing. We're just going to refit the model using all the available data. And here we have the results. So you can see the coefficient for advertising in this month, the coefficient for advertising in last month, which is smaller, so it has smaller effect when you go back in time. And the ARIMA part of the model is an ARIMA 102. Now we can use this for forecasting, provided we know what the value of TV adverts is in the right-hand side of the equation. So we can write the equations like this. So the regression part of it is an intercept plus the effect of advertising this month plus the effect of advertising last month plus an error, and the error is this ARIMA 102 model. So when we forecast, we need to put in the X's on the right-hand side. So for one period ahead, we'll need to know, we will already know this variable, which is the last advertising in the training data, but we'll need to know how much advertising we're going to expend in that month. So we're going to use a scenario approach where we look at what happens if we spend different amounts of money. So if we spent 20 on, 10, if we spent 10 units of advertising, this is what we get. So we're going 20 steps ahead. That's what that 20 is, how many steps ahead. And this is telling us how much are we going to spend on advertising in each of those subsequent steps. And if we did spend 10 in every month, that's what we'd get. If we spent 8 in every month, that's what we'd get. And if we spent 6 in every month, that's what we'd get. So we can come up with scenarios and plan appropriate advertising expenditure using a model like this.